going to share the screen. And well, before sharing the screen, now that I see you, I see your faces, I want to first of all welcome you all to this workshop. I will share the slides for a brief opening, but I wanted to introduce you to at least two of the organizers who are connected today. Sofia Seinfeld Tarafa from Spain, and Alberto Canavo from Italy. So since we are perfectly on time, I'm going to share the screen, and here, and please let me know if you can see this slide.
Yes, we can see the slide.
Perfect. So once again, thank you to this first edition of the 3D reconstruction, digital twinning and simulation for virtual experiences workshop. This is, I said, the first edition of this workshop, and I'm very happy that we received many submissions, and many quality submission could be accepted. I already introduced two of the co-organizers, but I want to mention also Bill Capralos from Ontario Tech University, Canada, and Zian Elvi from Uppsala University, Sweden, and Kindau Institute of Bioenergy and Bioprocess Technologies, China. So I'm really proud to be one of the organizers of this workshop, because actually we tried to put together, both from the point of view of the organizer and from the point of view of submissions and papers accepted, a good representation of what is going on this in this area, this field of 3D reconstruction, simulation, and digital twins, which are very related topic. I tried to summarize here some of the content from the call for paper, because I wanted to tell you what's the idea behind this workshop. So we actually looked at the workshop that had been organized in the previous edition of the conference, and we realized that some of these the keywords that are actually included in the title of our workshop were not fully represented in the current workshop. So we, of course, we span the whole continuum, virtuality continuum. And of course, we were ready to consider submissions touching all the key areas, also from the application point of view, like industry, healthcare, cultural heritage, smart cities, and education. And in fact, we did receive submissions touching from a more theoretical or more application-oriented point of view many of these areas. And we considered the field of interactive simulation, of course, related to virtual prototyping and to the impact that virtual prototyping can have on sustainability, on sustainable industry, on sustainable tourism. We were expecting submissions considering, for instance, telepresence as a way to be present somewhere else, for instance, for carrying out collaborative tasks. So the socialization aspects of virtual, augmented, extended reality technologies. Of course, as said, we were open to receiving submission concerning algorithms for simulating physical phenomena, but also to consider techniques for reconstructing the physicality of the experiences, also maybe for some experiences that consider also other senses. I mentioned tourism, so it was certainly of interest, the aspect of virtual tours, of navigations of these reconstructed environments, and also the idea of a distributed architecture for supporting digital twinning and 3D reconstruction put together to solve some problem or achieve some goal. Of course, we were expecting to receive submissions concerning presence, immersion, so stimulation of the senses, stimulation of the perception of the story from the point of view of the end users of these user experiences, in which 3D reconstruction and simulation are maybe used together, and also the aspects that pertain human-machine interaction with this digital twinnings of real entities, and testbed protocols and metrics for studying reconstruction, simulation, and digital twin experiences. So our idea was, and of course, all the technologies supporting this these branches. So our idea was really to see what's the connection between the three keywords, and I'm sure based on your submission, your contribution, that we were able and we will be able to provide a good picture of what is going on in this field. So I wanted to, of course, once again, thank you for your submissions, but here you can see how well we are also covering the various countries. We received, we accepted 11 papers, and we have authors from basically 11 countries. In some cases we do have overlaps, but in some cases we have papers overlapped from co-authored by authors of different countries. I think we have half of the works from the academia and half of the industry. So this is another good example of how well these topics are now widespread in all the domains. Coming to the program, as you have seen, since we have 11 submissions, we decided to split the program in two sessions. The first sessions will be chaired by Alberto, and I said we have 6 papers, and I have seen that at least 5 out of 6, if not all of them, the speakers, I mean, are already present, and so I think we are almost ready to start. The second session will start at 9:45, and will be chaired by Sofia. Of course, at the end, we have some buffer, so we might have some discussion, but let me tell briefly about the format of this workshop. So we were left free by the IEEE VR organizer to plan and decide how to manage this workshop. And so we chose to have presentations and Q&As, so question and answers held live. So you received the instructions telling that you will be given up to 10 minutes for the presentation and up to 4 minutes for question and answer. We are assuming that there could take some time for you to switch your screen sharing, camera, mic on, and so approximately 15 minutes overall. Of course, you were requested to send also pre-recorded video presentations. Some of you did basically a recording of his or her presentation. In some cases, we received more elaborated videos. So I want to stress the fact that these videos are just meant as a backup, only to be used in case of connection issues. These videos were uploaded by the authors on YouTube in hidden mode. We, Organiser, have the link, and we, the plan is to link the videos to the workshop program page at the end of the event. Basically, the page is already available, but we are really excited to see your presentation live and having you authors, speakers, responding to the attendees' question live, because I think it's we really need to go back to a normal, our normal habits, or at least to the new normality. That's it from my side. And I really want to thank once again all the authors for the great contributions, the co-organizers, and of course the IEEE VR committees, all the committees, for giving us the opportunity to organize this workshop and welcome you to this workshop. I would now leave the floor. We can wait a few minutes for the exact timing, but I will leave the floor to Alberto, who will be chairing the session. I think that, well, I don't know if you authors can share the screen, but we can maybe make a trial with the first speakers. Alberto, floor is yours.
Yes, thank you. So I want to take the opportunity of these minutes that we are in advance times. So I would ask if are present the authors of the first paper. In particular, I'm looking for Michele Russo from the University of La Sapienza in Rome. I cannot see his name in the participants. Are there any authors of this paper?
Yes, Michele is trying to enter, but he has some problems. So it is better that you share the video, and in the same time he try to enter.
Okay, perfect. So I will share my screen with the video presentation. Can you see my screen?
We can wait maybe a couple of more minutes. So if Michele is able to enter, he can make the presentation live. Otherwise, we can start. Anyway, we have at least one author ready to answer questions. So. Meanwhile, I'm asking some questions in the chat. So basically, if you registered for the event, you should have received a link. You are requested to access Zoom from that link, and then you need to create an account. I had my own account, but anyway, you have to create an account, and afterwards you enter the web page of Zoom, and then you see in some point of this page a section ticket, and from there you can join the main lobby of the conference. And there you'll find all the sessions that are running or going to start, and you can join them. This is what I did, so I just try to explain. I think that we can start now.
Okay, Just a brief presentation of this paper. Authors that come from Italy, several universities from Italy, University of Pisa, Padua, and University of Rome and Polytechnico di Torino, show some application of architectural heritage based on 3D reconstruction, digital twinning, and virtual reality. So if you can confirm me that, can you see my screen? I play the video that we received from the authors. I can play the video.
Yeah, we can see.
Okay, perfect.
There's no audio.
Oh, yes. I just stop and restart the sharing.
Good afternoon,
now,
everyone.
can you hear
I'm
the
Michele
audio?
Russo. It is a pleasure for me to present you 3D
Yes.
reconstruction, digital twinning, and virtual reality architectural heritage application on behalf of Professors Bevilacqua, Giordano, Russo, and Spallone. The cultural heritage complexity often characterize the buildings, the historical buildings in particular. The intersection between the architectural components and the historical transformation makes it challenging to understand the built heritage, not always accessible or still existing. In the last 20 years, the massive application of ICT to tangible and intangible heritage has profoundly changed the knowledge, fruition, and enhancement of cultural heritage. The integration with bibliographical and iconographical data allow creating a virtual replica of the cultural heritage assets and the efficient transmission of data, named digital twin. This knowledge model brings significant benefits in analyzing, preserving, communicating, and managing architectural heritage. In this scenario, research interest given by merging virtual reality and digital twin suggests a new way of approaching culture, focusing on data management and representation. The user is a dynamic actor able to interact and interface more easily with cultural heritage. It encourages knowledge dissemination to a broader audience, and it develops multidisciplinary research. Virtual reality refers to an extended container defined by precise steps in cultural heritage domain, as well as reverse modeling pipeline. All these interrelated passages pertain to architectures, to digital and computer science domain. Virtual reality in cultural heritage representation is an established practice. To visualize digital twins and environments, we're talking about the level of details and interpretation in accordance with the virtual reality aim, and to develop virtual tools to immerse and interactive users, talking about sensory enrichment for understanding and naturally interacting with spaces. The content generation in cultural heritage is central and critical because it involves experiential and cultural aspects, process traceability, and visualization coherence. The article proposes different experiences of VR in the cultural heritage domain using digital twin, highlighting VR as a tool for understanding, reading, and interpreting architectural heritage. The first case study we present concerns the provisional hall of the first Italian parliament, built in 1861 and demolished in 1865, an historical building belonging to the courtyard of the 17th century Palazzo Carignano. Its different possible locations and the presence of findings make it an interesting case study for the conservation and transmission of the disappeared architectural heritage memory. Data sources extraction, 3D reconstruction, and virtual IR VR representation are the key passage of this research. The virtual reconstruction involved a complex philological interpretative 3D operation based mainly on the coherence check and the interweaving of data from bibliographical, textual, and iconographical documents, by the verification, validation of hypotheses regarding the belonging of the building of wooden elements. For example, we are talking about capitals, balustrades, cornices, doors, found in the palace storerooms, and the coats of arms. At the end, the integration of the lacunae that are important to complete the idea of the building. The reconstructive model made up using rhinoceros is now the first and only product capable of restoring the three-dimensional image of the building and, through an immersive experience, allows the exploration of spaces that no longer exist. The prototype level of development of virtual reality made use of personal devices and cardboards. The digital model was reworked according to the type of experience with texture baking techniques for the generation of normal maps and ambient occlusion. The model thus generated was inserted in the Sketchfab web service for VR use, suitable platform for the aim of this kind of project. The second case study concerns the monumental complex of Charterhouse of Pisa in Calci, one of the most significant monasteries in Tuscany. Founded in 1360, after several modifications, it lost its original function in 1962 and hosts today 2 museums. The aim is enhancing visits to the National Museum of the Charterhouse through immersive VR experience. The 3D digital survey and historical analysis represented the research basis of this experience. 3D models were developed with the open source software Blender and Unreal Engine. The study provided a new tour path in order to expand the number of visitable space and to increase the immersive involvement of visitors, who are left free to move along the path using audio-video guides on tablets or smartphones. A graphic animation that you are looking in this moment in the slide of the wall 3D Charterhouse reproduced the external construction phases of the complex. Info pop-ups superimposed point out the building. The VR experience of the cloister of the chapter also to be experienced with the VR helmet, where viewers are immersed in virtual spaces that represent the layout of the cloister in its most important historical phases. A narrator voice accompanies the visitors during the experience, describing the various evolutionary phases.
There is some problem with the video.
I think that it crashed.
VR experience in the chapter of, and in particular in the chapel of Sant'Antonio, about the quadraturist Pasquale Cioffo, that was a painter from Naples. It is an experience focused on the painting techniques, explaining the geometric principles underlying the representation, and providing a 3D reconstruction of the illusory space depicted, inside which the visitor is immersed thanks to the use of the VR handset. The story then focuses also on the optical phenomenon of anamorphosis found on one of the sides of the chapel. The third and last case study deals with the virtual reconstruction of the Renaissance Cathedral of Carpi, designed by Baldassare Peruzzi and documented by a urban view. In particular, you can see in the slide the second half of the 17th century by Luca Nasi. This is the central theme of the exhibition organized by the Museum of Palazzo del Pio in Carpi. Peruzzi made a wooden model to explain to the masons how they built the cathedral. The model disappeared in the mid-17th century, starting from the precious document integrated with paintings, prints, written memories, description, archival docs. The digital reconstruction of the cathedral was realized not as a simply instrumental model, but as a critical interpretation process related to the architectural design genesis. The implementation of documents data testifies the importance of a multidisciplinary approach in this interpretative test. The virtual reconstruction of the lost wooden architectural model has been communicated through an app of ER so that the visitors could admire it loaded on a tablet. When visitors framed the map of the church with the tablet, a wooden model faithful to Peruzzi's project appeared on the screen. VR is planned to be tested in the near future. In conclusion, we have seen 3 case studies showing VR as a new model of knowledge for cultural heritage and bridging with digital twins. A key critical role of digital content has been highlighted in both all the 3 case studies. The projects are in the testing phase and planning future validation to enlarge user domain and testing VR communicative impact. Surely, visualizing and understanding architectural space and time transformation in immersive, interactive, and engaging way leads to an improvement in architectural knowledge, democratizing audience of user. At last, the growing interest in VR for cultural heritage frames its critical role in the future, supporting knowledge and understanding process of these environments. I thank you for your attention. Good afternoon.
Okay, thanks for the presentation. And I think we can start the Q&A. So if audience have some questions, can write them on the chat or can switch on the microphone and say the question directly to the authors. So I would ask if there are some questions for the authors. I think there are no questions. Just one my curiosity. You reported in your presentation, you reported 3 examples of using virtual reality and augmented reality technology. So my question is, have you observed some differences in terms of, for example, of acceptability between these 2 different technologies? In terms of both acceptability from the side of the staff of the museum or historical place and audience and people that possible user that can enjoy this technology.
Yes, I try to answer, but I know I don't follow the experiments in the Museum of Carpi or in the Certosa di Calci, but I have a personal opinion about this issue, and it is that when you are in a museum, perhaps it's preferable to overlap to the reality some other information using AR. I prefer this way to share and use the heritage, because when you are on site, the mix of reality and virtual could be a more involving experience. And then when you are on site and use VR experience, you are a little bit distant from the environment in which you are. The advantage is certainly that you can perceive the space, the 3D space, 3D model space in a way that is similar to the human perception. So there are some points in favor and some points that are not in favor in respect to AR or VR.
Okay, thank you. Thank you for your answer. Are there any more questions for the authors?
Well, I have one, if there's none others. My question would be, if I can ask for the performance that you're getting in these models, because I've seen quite a lot of geometry involved in some of them. So if I can ask roughly what would be the average parameter was the hardware used to present it? Thank you.
I have heard only a little, so if you can repeat, because the audio for me is not good.
The question is about the performance of the virtual reality application. So if you can provide more detail about, for example, the models or the complexity of the models used in your application. I get your answer, Fabrizio.
Okay, it's clear. In the first one, the model is simplified because the experience is made through a simple handheld mobile phone. So the model is uploaded on Sketchfab. And the mesh is simplified. The reconstructed 3D model is much more complex than that we use for the experience. In the other experience, I saw, because I'm not involved in the other experience, but they are used inside the museums, and I saw that they are realized using more performing tools such as tablets and so on. So I think that the models are more complex, could be more complex. In other experience, using AR, not VR, the model could not exceed the 100 megabyte, not the model couldn't be heavy.
Okay, thank you again. I think we need to move to the second presenter. The second paper is entitled Photocamera Bot, an autonomous ROS-based mobile photography robot for precise 3D reconstruction and mapping of large indoor space for mixed reality. It is presented by Soroush Montezapor. He is from the Virtual Reality Research Group of TU Bien. Austria. I see you, so I can leave the floor to you for your presentation.
Actually, I still cannot share screen. It says it's host disabled participant screen sharing. So
I think you need to enable them, Alberto, because I don't know why you probably, or Sofia is the main organizer. So
okay,
you need to go on the participant list and give them the rights to do that.
Yes.
I think.
Just 1 second.
Either you or I think it's to avoid that anyone can share at any point in time, but can either you or Sophia do the...
Yeah, I'm checking whether I'm the one responsible to allow him. Let's
Also,
see.
yeah, only you.
Okay, I think, okay, so only one, okay. Oops. I have changed a configuration. Can you try now to see whether now it works?
Yes, it seems that it's going to work.
And then it seems that only you, Sophia, are marketer or organizer. Maybe you can also...
Okay. I don't know why, but okay.
But maybe you can enable all the authors so that...
Yeah, now I have enabled, I think I have enabled all authors. If it doesn't work out, then I will check what's happening. But I think I clicked something and now it should be fine with all authors.
Thank you.
Okay.
Sorry for that.
Yeah. Do you see my screen now?
Yes.
Okay, perfect. Yeah, hello everyone. My name is Sarush Mortezapur, together with my colleagues from the VR research group in TU Wien, Austria, and Illusion Walk company in Germany. We are presenting and proposing Photogrammabot, which is an autonomous ROS-based mobile photography robot for precise 3D reconstruction and mapping of large indoor spaces for mixed reality. My talk today will be divided into an introduction to the problem, then we will see some related work in comparison to Photogrammabot. I will explain more and describe what Photogrammabot is and our proposal. Then we will see some evaluation approaches and results. And at the end of the presentation, I will make a conclusion out of the discussion. Generally, creating content for mixed reality is always bothersome because the 3D models of the objects need to visually blend well with the real object and real environments. Luckily, photogrammetry can facilitate this process. Photogrammetry is capable of reconstructing textured 3D models of environments and subjects using a high number of photos taken from different angles and different distances to these subjects. Not only reconstructing textured 3D models, but also photogrammetry can help calibration of tracking system as it is explained in immersive.Dec. Immersive.Dec is a concept that was first introduced in 2016 as a large-scale wireless VR system for multiple users. Well, multiple users were able to walk freely in a room, and the ceiling of this room contained many fiducial markers, and each of these users had an upward directed camera mounted on their own devices, so the cameras could see the fiducial markers on the ceiling and localize this user in this environment. But photogrammetry in general needs as many photos as one can take because the number of correct photos correlates directly with the quality of the result and consequently the precision of the 3D reconstructed model. Photos need to have sufficient overlap so they could be registered by matching features, and one would need close enough proximity photos for details to be detailed. If a human photographer wanted to take photos for photogrammetry purposes, one would need, of course, experience and tools in order to determine the best positions and angles for taking photos for this purpose. They should spend a lot of time. And in case of indoor photography, because especially if your area of interest is the ceiling, one needs to hold the camera as close to the ground as possible in order to get sharp images without any distortion. By nature, photography phase of photogrammetry is made of repetitious tasks, and we can all agree here that robots like Photogrammabot are very efficient and effective in such repeating tasks. There's been many successful attempts in order to utilize robots for 3D reconstructions, like remotely controlled sensorized car that was initially introduced and proposed by Toshi and the colleagues, mainly for outdoor 3D reconstruction. Compared to remotely controlled robots, we have autonomous mobile robots, which are more efficient because they need less human effort, and one subcategory of robots which are very popular and gaining more popularity every day for 3D reconstruction are UAVs or drones. Compared to each of these categories, Photogrammabot brings some benefits. For instance, compared to remotely controlled robots, Photogrammabot needs minimal human effort because it is completely autonomous. Also compared to AMRs, which are proposed so far, it is capable of providing very high quality textures. Well, usually most of the autonomous mobile robots which are proposed for 3D reconstruction can only provide colored point cloud, not textures. And also in most of the works, the robots which are proposed are considerably expensive, like the one you can see on the right side, PR2, with many high-end sensors. But compared to them, Photogramma is completely affordable. But with the main rival, which are UAVs and drones, Photogramma has considerably longer operation time, and it can handle significantly heavier payloads, which is very important if one wanted to use a camera with larger sensor or larger objectives. Actually, cameras with larger sensors and larger objectives are beneficial in indoor photography due to insufficient amount of light. And also, if we want to use drones for indoor photography, a drone that can handle heavy cameras, these drones produce heavy amount of wind, which is not preferable in indoor environment in many scenarios. As mentioned, Photogramma is an affordable autonomous mobile robot that utilizes Robot Operating System, or ROS. It can take photos from different angles, thanks to its adjustable camera position, and also it is capable of handling different cameras. By itself, Photogramma is made of a mobile base, a Raspberry Pi as the computing unit, an onboard computer, a 2 degree of freedom micro turret that adjusts the pan and tilt of the camera, a normal point and shoot camera that could be controlled using the onboard computer, and a 25-meter range LiDAR. In software, Photogramma uses a greedy frontier-based exploration algorithm in order to explore an unknown environment, and uses SLAM to create a 2D map of this environment. After creating a map of the environment, it creates a path made of many waypoints, and the robot starts taking photos by traversing this path, stopping at each of these waypoints, adjusting the orientation of the robot and adjusting the orientation of the camera, taking photos until the entire room is covered. After covering the entire room, the photos are then used for photogrammetry and creating the 3D reconstructed model. I should also mention that all source codes of Photogramma are publicly available on GitHub. In order to assess our robot, we have tested the robot in a room that was slightly larger than 200 square meters with 400 fiducial markers distributed on the ceiling. And the robot was able to capture 1,386 photos in 4 hours of operation. Then these photos were used for 3D reconstruction, and they were compared with the laser-based ground truth using triple track tracking system that uses in an iteration that uses 3 random markers to create a coordinate system and to match these 2 models based on this coordinate system and compare them. The result of the comparison is that the marker position accuracy was between 2 and 5 millimeters, which was quite acceptable for our application. And also the corners of the room, the 3D reconstructed room and the ground truth, had an average deviation of 2.2 centimeter for such a room, which is again acceptable for our application. At the moment, the robot is capable of providing 6 hours of operation time, although the amount of time that was needed by the robot to capture around 1,400 photos was more or less near the amount of time that a human photographer would need. I should mention that we have limited the speed and acceleration of the robot to 20% of its actual maximum in order to reduce the risk of introducing errors by mechanical parts. So increasing this amount, of course, will also increase the whole process, to increase the efficiency of the robot. To conclude, the evaluation results showed the fitness of Photogramma for the purpose that we had. Also, Photogramma is capable of providing good quality input photos for photogrammetry. It could help with the mapping of fiducial markers for marker-based localization. It can reduce human effort considerably, and also for some applications like what we have, that we need to scan remote sites very often. It is much easier to transport a foldable robot than a human photographer to remote scanning sites. One of the future works that we are going to work on is multi-room and multi-story building 3D reconstruction. For multi-room 3D reconstruction, basically with the same setting and with the same algorithms, the robot must be able to scan complete an entire floor and 3D reconstruct that floor, although we have never tested in a multi-room setting. But for a multi-story building, one would need to augment a robot with the capability of climbing up and down stairs in order to go into different stories, different floors, and take photos. This was all I had to say for today's presentation. Thank you for your attention. And if there's any questions, I will be more than happy to answer them.
Thank you for your presentation. Are there any questions from the audience? Oh, yes, there is one question in the chat. I read the question. Super interesting work. Thanks for the presentation. How does photogrammetry compare to laser scanning in terms of reconstruction fidelity and scanning time? And the second question is, also, I am interested in the algorithm used to create the plan before taking photos. Where can I learn more about it?
So the first part of the question was about sorry, what was the first question?
The comparison between the laser scanning. Yes.
Yeah, laser data. Basically, laser data are faster than photogrammetry, because photogrammetry is not just about taking photos. After that, you will need hours and hours of processing in the computer, especially a powerful computer. So in terms of amount of time that is needed for 3D reconstruction using LiDAR data, 3D LiDAR data, or using photogrammetry, of course, LiDAR is much faster. But in terms of quality, they are, again, not comparable. So the quality of photogrammetry is much higher than laser data. Okay, and the second question is about the planning phase of the robot. So can you provide more details or more help in understanding this topic? How can we learn? Well, of course, actually, planning, I take from the question that planning means the planning phase. So after the mapping is done, so the robot needs to plan a path in the environment in order to follow this plan and also take photos. Well, basically, there are different approaches. The one that we took was the approach of a spiral, a wave-shaped path that is very simple because it could answer our needs. But there are also other approaches like finding best view, which needs more computation, of course, and will need more time. And this will reduce the operation time of the robot if one wanted to use best view algorithms for this. But I would say this very much depends on the application. And if you are, for example, scanning one room like what we are doing now, or you are scanning a floor made of many smaller rooms and hallways, in each of these, this is different. But in general, I think in robotic communities, there are thousands and thousands of papers about how to plan a path in an environment. Thank you. Just very quick question is my curiosity. Have you considered as future work the possibility to exploit multiple robots in the same room just to reduce the time of the taking of the photos? How much effort should be put for combining more information about more robots coming from multiple robots? Well, if you have never thought about it, but this is an interesting idea, multi-robot installation setup, actually. But robot operating system, one of the good things about robot operating system is that many of these questions are already resolved there. So you can have multiple robots scanning a single room, and they share the map that they created out of the room, and they can exchange data easily. And at the end, I think this is quite possible. So if one wanted to have the result, the images sooner, or they want to scan some room that is larger than what we have now, that is not possible to cover in 6 hours of operation, then of course this is a good solution. So well, yeah.
Thank you again. We need to move to the next presentation. Thank you again, Sarush. The next presentation is presented by John Picker. Authors asked me to show the video. So can you confirm that I can share your video, because I see the
please.
authors?
Thank you so much.
Okay.
This
so
is super
now,
helpful today.
yeah. Okay, I will share the screen now. Just 1 second.
Thank you, Alberto.
Okay, can you see the video? I forgot to share also the audio, so just 1 second. Okay.
Thank you so much for joining this presentation today. I wish we could meet in person these times. Today I'm representing the work of a research team. I'm coming from 2 universities, Graz University of Technology and the University of Applied Sciences in Vorarlberg, representing, also my name is Johanna Birke and I'm representing Enrique Loria, Said Safikani, Andreas Künz and Sabrina Rossmann. We were interested to looking deeper at the state of the art in the literature through a literature survey to identify interesting use cases, application fields and technologies combining digital twins with virtual reality. So just to quickly summarize our main research questions in this field, and I just big spoiler ahead, 10 minutes will not be able to cover all the details, so please read the paper if you're interested in. But the main research questions we focus on, we want to find a little bit, is this like a relevant research field these days? Are there many publications? Is the number of publication growing? What are the main application fields? What are the main use cases combining VR and digital twins? What technologies are used, and especially what are potential issues and problems and future roadmaps we could be interested in. The methodology we use is a literature review following the PRISM guidelines. So we focused on the 3 following libraries, ACM, Scopus and IEEE Explorer, because ACM and IEEE Explorer is one of the venues for relevant research in the field of VR, conferences such as IEEE VR, VRSD, ISMAR, and Scopus does also include quite a lot of research in this field, but also in the field of digital twins. So that's why we focus on those 3 main libraries. And we only looked at English papers, peer-reviewed papers, and used a search term combining virtual reality and different versions of digital twins. What you can see on this slide is that in the beginning we found altogether about 515 records, but after removing duplicates, after screening them, reading abstracts, reading the whole paper, in the end we found only 30 studies which were relevant based on our evaluation criteria. And already looking a little bit at the first research idea, we can also see that most of those papers were written between 2008 and 2021. This is of course also because the term digital twin is relatively new. There could be, this is already one of the main limitations of this work, a lot of other works in the past describing this topic, but the wording digital twin might not have been used explicitly in this paper, but the technology might be pretty much the same. And what you can see that it is a interesting field, but yeah, there is quite a lot of room of improvement for presenting more studies in this field in the future. In terms of application fields, This might be not super surprising, but the most papers were written in the field of Industry 4.0. This is the main application fields. A lot of interesting use cases describing like for factories, but also combining eventually the work of robotics, of engineering, but also training, education. I think those are all the fields where we sort of do expect digital twins. We present the examples in the paper. Please read the paper for details on that. What might be surprising, however, are fields like gastronomy. So quite interesting. And one small example here would be a digital twin of an ice cream machine that you can learn how to interact with this ice cream machine. So this is something which is quite fun to look at. Of course, health can be an interesting example, also in the field of surgeries. Aerospace, by the way, is one really interesting topic, not only for digital twins, but especially for virtual reality. So especially in the field of aerospace, there has been already many years of experience in the development of digital twinish environments, even though they were not called that way, but especially also in the field of virtual reality. So what use cases were described? So in terms of use cases, I mean, there's a little bit of an overlap. What is the application field, but what is the use case? But we were excited and to identify use cases to explore which explore this topic. And before I start describing the use cases, I want to quickly summarize also the advantages described by the authors when using virtual reality in combination with digital twins. And these were especially things like it's low cost, it supports advanced visualization methods, and especially this immersive 3D environment. It allows natural and direct interactions with the twins. It allows advanced controlling and data collection methods. It's very portable. It allows remote usage. It's very scalable, and it also allows augmented use. So, for instance, that you have additional information about the twin, and of course, it can be real time. The use cases described would be, for instance, for evaluation and user studies. So digital twins can provide a very safe environment to assess behaviors and processes. But of course, remote operation, many use cases of remote operations have been described, because especially through this intuitive interface, it's often nicer than looking at the 2D screen and interacting with the machine in a not super natural way, but rather through natural and intuitive controls. And remote collaboration and guidance. So many traditional digital collaboration tools split the person space and the task space. The person space would be this verbal, non-verbal cues, and the task space, the space where they work together. And here in a virtual reality environment, you can really create something which is very fast and productive instead. And it allows a really lovely place for co-located collaboration and communication. As an education and training tool, and I don't think we need to go deeper into that. Virtual reality has been always quite successful as an education tool. And of course, if you work with digital twins, you can really learn how to work with this machine, for instance, in a very interesting environment. So digital twins in VR to support understanding and decisions. So for instance, one example would describe how they plan this shop floor layout and create a collaborative system for decision makers to understand the situation better. And what I found quite interesting, that it can also be used as a corner case for authoring and design, because you have this spatial and three-dimensional interaction in VR, and it's a very relevant tool to display digital twin environments and author and configure them. In terms of technologies and directions forms, in the papers we used and analyzed, most of the authors described the use of the HTC Vive environment, many also the Oculus Rift. Only a few, however, the Oculus Quest and then mobile VR. This could be certainly because it's a relatively new technology, the Oculus Quest, for instance, and mobile VR probably does not come with the capabilities to support the visualizations of digital twins in VR. Just one idea. And yeah, as a last point, I would love to talk about the challenges and issues, because this also leads to the roadmap. And the main challenges identified by the authors of those papers were cyber sickness, the acceptance of the technology, that there were a lot of missing evaluations, and especially evaluation techniques are missing, network challenges and communication traffic, the security issue, and that it's the hardware to actually access those machines is often missing to make a natural and intuitive interaction possible. To sum it up, we talked about the limitations, especially the missing limitation of the missing definition of the digital twin early on. Potential future roads could be, especially in the fields of exploring new user domains, providing new user studies, working on the field of network communication improvement. What I find super interesting is this natural interaction between the systems, work with new devices, and explore more data analytics options. So we looked at 30 papers, identified various fields, the advantages, use cases, and the challenges. And to sum it up, it's a very important field, and I think there's so much more to do in this field. We're super excited to be part of this research, and if you do have any questions, please just write us an email. Thank you so much for attending this presentation. Thank you.
Okay, thanks for the presentation. Are there any questions from the audience? Okay, I think there are no questions. Just one very short question. It's a very interesting survey. So thanks again for this work. My question is about the future. So in your opinion, which could be the application domain that could benefit more from this technology, from virtual reality and digital twin, in your opinion? So after reading 30 publications and reading some these papers.
Yeah. Thank you for coming up with this question. A very interesting one. To be honest, I feel especially those which are not so much covered yet, because I mean, I think we can see the potential for Industry 4.0 quite a lot. But for instance, also finding an example in gastronomy, I found really exciting. And to be honest, like the term digital twin, I mean, there are a lot of previous work papers out there which sort of cover this topic, but did not use this wording. But I think there are a lot of inspirations out there how this can be used. I personally love it for the field of training and education. That's also where we love to work in. But honestly, this is a space which is still so open. I find it super exciting. By the way, Andreas Künz will also present a paper on AR and the potential for digital twins on Monday at this conference. If anyone is interested, where we talk a little bit more about the augmented reality aspect of this. Sorry, I'm constantly losing my voice.
Thanks again. Okay, so if there are no questions from the audience, we can move to the next presentation. The next presentation is entitled Challenges of Experimenting with the Virtual Reality. And the presenter is Christopher Skutworowski. Sorry for the bad pronunciation. I'm very sorry. He is from the Technological University of Dublin, Ireland. So I leave the floor to the next presenter.
Okay, hello. Sorry, because if we actually would be there, where we're supposed to have this conference, then I could wear a t-shirt. Unfortunately, it's chilly.
Yeah.
So I have to go back to now.
That's great.
And just a word, this is going to be more fun presentation. Okay, so oh yeah, I have to do the share screening. 1 second. Where is this option? Share screening. So that's the right one. You got it?
Oh, yes, we can see your screen.
Awesome. Okay. So hello, I am Krzysztof Szczurowski. I'm a PhD student at the Technological University Dublin, and I'm trying to develop an objective measure of presence in mediated environments. My supervisor is Dr. Matt Smith. I have been developing VR software for a few years now, and today I'm sharing some of the lessons that I've learned while experimenting with VR. So the lesson 1 is, before deploying your experiment, test it on users without experience using VR to avoid surprises. For example, I discovered that participants can press the HTC Vive menu button completely by accident when mounting on the VR headset. During an unstructured debriefing of pilot participants, I asked how long he thought he was in the virtual replica of the physical environment, and I was very impressed with the accuracy of his answer. When I complimented it, he said it wasn't difficult to keep track of time with the clock, and my reply was, what clock? So beware, the power button can overlay the menu over the content that you plan to display to your participants, and you might not see it on the back end if it happens on the HMD hardware side. I recommend disabling any buttons that are not essential for your experiment. Another thing is that to some of my participants, mounting the VR headset was more challenging than I anticipated. Some of them managed to complete it in a few seconds, others needed more than a minute. And the main thing is that if you will be using time series analysis, keep it in mind that lengths of the time series for such tasks might differ widely between participants. And if we are on the subject of time, beware that timestamps can be formatted in different ways, which can be a surprise when you are merging data on a timestamp from different hardware. In my case, it took me a while to figure out why I could not align data from biometric sensors with data from the computer used to run the experiment during the analysis. In general, I really recommend reading the documentation. It takes time, but it can save your experiment from discovering errors after you collect your data and find the problems during its analysis. For example, instead of instantiating a new color grading object in post-processing stack every time I was changing saturation on an image displayed to the participant, I should just override the existing one. It can take some time to generate a pile of garbage that will have an impact on performance. So before deploying your experiment, make sure you test your software for the maximum length of time your experiment might take in the worst possible scenario. And remember that RTFM rule really does apply in software engineering. Okay, let's move on to tips and tricks. Users' well-being is very important for the VR industry, and rightfully so, but to the point that heavy restrictions are being implemented into engines to protect them from mad and all incompetent developers. However, to carry out your experiments, sometimes you need to find some ways to go around such restrictions. For example, the field of view and control over refresh rate had to be modulated to investigate participants' physiological responses to such processes in my experiments. However, control over these parameters was disabled on a version of the Unity game engine that was used to develop software for these experiments. In case of the participant field of view, I just overlaid a rectangular over the camera to obstruct the participant field of view when I need it. And by controlling its size, I managed to easily go around this obstacle. The refresh rate was a bit more complicated, but I threw a wait for second object onto the main thread, and the waiting time was adjusted based on the rendering time for the last frame, but it did work like a charm, although bear in mind that disabling pacing can create additional screen tearing problems. Next lesson, would be that the computational mathematics can be expensive with complex geometry. In one of my experiments, I was using a cloud component, which needed more subdivision to render more realistically for recreating movement of the walls of the marquee that was used in this experiment. In the high fidelity version, the model had almost 65,000 of polygons and 40,000 vertices, which is not a lot, but was literally designed to make it easy to render. But the low fidelity version had below 2,000 polygons and a bit over 1,300 vertices. And with the normal maps being used, the marquee walls and roofs were practically indistinguishable when they were remaining static. Next thing, parameters that are important to monitor may be displayed through the user interface available to the experimenter, which is something I would very highly recommend. Next. Widescreen. Oh, that's a proper blue screen of that. 1 second. Okay, back in game. Dynamic lights and shadows are computationally expensive, but are not necessary for static objects. This can be baked in advance. And to increase replicability of your study, I recommend developing the software needed to conduct it with support to a broad range of VR headsets and other hardware, like sensors, etc. It might be available at different labs. And for the same reason, I advise to try to provide as much backward compatibility as possible. Obviously, it is not feasible to support the sort of demo class or all VR headsets that were ever made, but it can be a holy grail on the list of objectives during the software development for your experiments, which should also increase the capacity of replicability of your experiments. Now, publishing your code written for running the experiment as an open source should also have reproducibility and for the development of your research. And I also highly recommend following the open science framework and obtaining permissions from your participants to publish anonymized data to give other researchers an option to analyze it in the way they see most visible or to facilitate meta-analysis. Thank you. I'll try my best to answer your questions now. If there are any. Just gonna keep that going.
Oh, thank you. Thank you for the presentation.
Any questions?
Any question from the audience? There is one question. Can you see my? Okay. No, it's not a question. Thanks for the presentation. What was the most unexpected way someone broke an experiment of yours? This is a question from the audience.
Okay. The most, it's not directly related to this particular trend, but the biggest surprise that I had was the amount of impact that putting on the headset will have on participants' skin conductance. It's technically it's just a little bit of movement, tiny bit of movement, that's all that's needed, but it pretty much, like the amount of skin conductance that was increased by that thing, like it took about 2 minutes for the skin conductance to return to normal. And I wasn't anticipating that at all. Luckily for me, the next part of the experiment was crossover design, so at least this error was evenly distributed between the control and the intervention sections. But like it was really close to just completely ruining the whole experiment. Just putting the headset on and the amount of impact it had on skin conduct. That's the main thing that I would love to share. So it's a great question. Thank you.
Thank you. There is one question from Sophia, I think.
Yeah, more than a question, I just wanted to tell you thank you as someone that has already, I have also run a lot of VR experiments, and I think that all the tips you have given us today are really, really useful, and I have came across exactly all the problems you're describing. So really read this paper and follow the the advices. I even had once one participant that I told him, please close your eyes just to open the application. And then I forgot to say, open your eyes. And then the whole experiment, he was closing his eyes. So yeah, so thank you very much just for this, you know, simple guidelines, but important. And that's it.
Yeah, simple but kind of important indeed. Yeah, thank you.
Definitely essential.
Yeah, yeah. Just one question for you is about categorizing user. So if you planning maybe in the future work to conduct study exactly for one specific target, for example, novice VR user or professional VR user, because in my experience, also professional user can have some issue when experimenting some virtual reality system, for example, because they are not aware for that particular kit of virtual reality system or something else. So if you plan this future work.
Okay, so to be honest, the main difference that I would see here is between people who literally work in the VR sector and people who just use it for casual reasons. So like, even if you do have some hours clocked in on your VR headset, it's a different story if you've spent months or years developing software or testing software. Like it's two different ball games at that point. So in my case, I honestly don't see much difference. Technically, you can use qualitative methods. So you can ask the person how much experience they had. And that probably would be the best option here. And then you can even try to find some correlation between this parameter and other factors that you're evaluating. Yeah, but in general, I'm mainly referring to making sure that you don't just test it on people from your own team, because you have quite a lot of development, a lot of experience on the belt. So, and the tolerance is much higher. Like, so for example, for me, when the simulation drops down to like 10 prints per second, I'm still fine. For a lot of people, when it drops below 50, it's getting into dodgy area. Yeah, so it's just try your best to ideally borrow someone from a different department who has nothing to do with VR, and just before you deploy it in full scale as an experiment, just run with them and then have a sit down for maybe 5-10 minutes to literally just query all this sort of stuff that just giving them an open question so they can kind of tell you about the experience. So like, for example, this one with the closed eyes, technically speaking, they could go through the whole experiment with the eyes closed, and if you wouldn't ask afterwards, then you wouldn't even knew that the eyes were closed. Like,
yeah,
little errors like that can be quite important.
Okay, thanks again for the very interesting talk. So we can move to the next presentation. The author asked me to share the screen, so I just asked him to confirm if I can share the screen. The author is Yongkang Xin, and the purpose is design virtual reality training system for children with attention deficit hyperactivity disorder. I can share the screen. Can I share the screen? Yes.
Thank you.
Okay, so just 1 second.
Greeting for everyone. My name is Yongkang Xin and I'm from Guangdong University of Finance. My research topic is designing VR training system for the children with the ADHD disease. Here is my presentation content that will be include the introduction, talking about the background research, and then that will be about the framework overview on my VR system, and then there will be a small demo video, and the fourth one with talking about the future work. The first section is the introduction. At first, we talk about the background. ADHD is a very common mental disorder in children with a reported 5% global prevalence rate. We realize that the VR technology can play a very important role in the ADHD medical care. Our objective is to use the VR technology to help the children improve their concentration in the training. What about the innovation point? There are many existing VR projects dealing with this. We want to design a smart training working flow. Use the EEG brain electronic sensors to receive the real-time information feedback from the users, and then the mobile application can receive the EEG data from real-time and then get the data visualization to assist the medical staff and the patient's family in evaluating the treatment. The second section is the framework overview that will be about the design process, concept, and then the system development and interactive environment, design, measurement, mobile application. The first one, we need to talk about our design concept. In our concept, we does not only focus on building a single interactive environment, but also design a smart measurement flow to assist doctors and patients' families to monitor the patient circumstance in real time. As you see, here is the smart exploration and the flow concept. At first, the ADHD student will explore in the VR training system. The VR training system will provide some interactive environment that will be included indoor and outdoor environment. There will be some distraction elements. The ADHD children need to complete the concentration tasks. During the concentration tasks, the system will measure the data, and then the data will transfer by the EEG sensors. The EEG sensors data will send to the mobile application. And then the mobile application will let the data in visualization. The doctor can monitor the data for the mobile application at the same time. The patient family also can see the data. So both the doctor and the patient's family can know the current stage about the children. And then the doctor can customize the training process and the training process or methods to improve the whole training for the ADHD children. The second stuff is talking about the system development. At first, we need to build in the environment, so we need the 3D Max and the ZBrush, and then we need to build a system. This time we use the Unreal Engine, and then some interactive function we need to build, we use the C++ and the blueprints. Right now we discuss about the interactive environment. This research simulates the outdoor and the indoor environment, both two separate. At first, if we talk about the indoor environment, there will have some distraction element. There will be rodents, car, noisy classroom, wind sound, and also some movement like walking, people, and also some fallen leaf. And then the children will need to finish some simple tasks like the number selection in the right figure and the puzzle or some calculation. And then after the children finish the indoor environment, we talk about the outdoor environment. The outdoor environment is in the lakeside. It has some sound like the wind sound and some movement like the animals and some fallen leaves. This environment is going to provide a very beautiful science to smooth the children's nerves in the system. In that environment, children don't need to do any very complicated tasks. They just need to track the highlighted animals, that's all. So both two environments, we want to help the children to improve their concentration. After we finish to design the environment, we need to talk about how to measure the data. We group the VR device and the EEG headset together. Use the EEG headset to collect the brain rate. Here is the middle figure and the right figure. And then we will use the mind viewer, this software, to get the data. And then we can load the state of the device, the user's data in the real time. After we got everything data, we need to transfer to the mobile application. The mobile application can provide the patient and the medical staff with real-time data visualization and allow the patient and the medical staff to receive the data and address the treatment on time. The right figure is our prototype for the mobile application. As you see, we can receive each key important information and the data from the EEG sensors. And then we will show our demos. Here is our demos, and you can have a look. Here is slide is in the classroom indoor environment, show how the distraction element, and then finish the task like the number selection. The final part is the future work. Because our current stage for our research is still in the position, so we need to talk about how future work, what we will do. At first, our research right now still lack of the user test, so we need to run the large group of the user test, especially for the children, to receive the user feedback, and then we will optimize the user interactive functions and throw the feedback. And then the second step is the continue developing the mobile application, because right now the mobile application are still in the initial stage, so we continue to improve that and then maybe provide more assistance or maybe more function in the mobile application. Thank you everyone. This whole my application, and if you have some questions, just let me know.
Okay. Thanks for the presentation. Are there any questions from the audience?
I have a question. Well, first of all, thank you, Yong Kang, for the amazing presentation. It was a very, very interesting topic. I just have a quick question regarding your research design. I'm wondering why the lakeside was actually chosen at the outdoor environment, as opposed to, for example, other environments like a park or a schoolyard that students could be mostly interacting with.
Yeah, when I design the outdoor environment, at first we want to design maybe a crowd people noisy city, but we think it's for initial stage for the children. That will be too complicated for them because there will be many buildings and too many people if we design the park or the city. So we select the outdoor environment. So the ADH students sometimes is lack of the outdoors to have a sightseeing or traveling, and also this chance is also an opportunity for them to provide a smooth environment and smooth the visual effect. Yes, thank you.
Okay, thank you so much. I have just another quick question as well. How can we access the mobile app that you mentioned?
Mobile application is right now what we can do is because we set a client in the desktop side, where in the desktop side we see the EEG sensors, the data, and then that server is directly feedback to the mobile application. But the mobile application right now only can show the data visualization because like some recording or the log, some kind of the function has not finished yet. Just display the data visualization only right now. Yeah, thank you.
Thank you.
Thank you. There is one question from the chat. It is a Yuxuan that thanks you for the great presentation, and he is wondering if the system have any support for real-time adjustment from the doctor side. So if there are anything that the doctor can do with the real-time data collected during the use of this system.
I mean, I just checked the question. Yes.
Yeah.
Real time. I think the real time data is what we put. One is to the children can do it in at their home, and so that the doctor can check the data. So right now, I think our function for this project, and they can make the adjustment in real time, just check the data and then make the feedback after they come back to see the doctor again. Yeah.
Yes, maybe the system can adjust its status, its condition according to the feedback collected from the doctor's side.
Sure. Yes, sure. Because as you see in the indoor environment, there will be a few tasks. Some of them, the number selection is very basic task. After the doctor check is number selection, they're very good for this task, and then they will go to some calculation and the puzzle selection, and the puzzle the number will be more and more and complicated. So yes, the task will be complicated when they finish the simple task, and then they move to more and more complicated. Yeah.
Thanks. Thank you again.
Okay. Thank you.
Thank you. This one. Yeah.
My question would be, because if I understood correctly, you had 4 sensors on the EEG, and they were all on the prefrontal cortex. Could you tell us a little bit about potential problems with the EEG, with the EEG headset like that, and the VR headset kind of operating at a close proximity?
Yes. So the EEG, we blind them in the HTC Vive. That should be in here. I think it's in here, because I'm not that part of how they bind them. So and then they check the system. But when I use this one, and sometimes we will have some noisy problem. The noisy problem will be sometimes if it's not very suitable. So we still want to adjust that because if the children need to weigh at home and they need to know this is weighed correctly, so we still want to figure out a better solution for it. But right now still have a small problem, is that the noise is a little bit high. Yeah.
Okay.
Thank you.
Thank you. Thank you again. We can go to the next. We can move to the next, to the last presenter of this session, and then there is a little break. The last paper is entitled "Lightweight Collision Detection Algorithm in a Web 3D Robot Simulation Platform." It is presented from Wenqing Wang. He presenting a joint work between the Tongji University in Shanghai and ETH Zurich in Switzerland. So now I would ask the presenter to share his screen.
Hi, can you use my video in the presentation?
Sorry?
Hello, can you hear me?
Yes, I can hear you. Yes.
Okay, can you use the video in my presentation?
Okay, so give me just 1 second to switch again.
Hello everyone, my name is Weichang Wang, and I'm one of the authors of this paper entitled Lightweight Collision Detection Algorithm in Web 3D Robot Simulation Platform. In this paper, we are proposing a novel bounding volume hierarchy with the molten code collision detection algorithm on the browser, which combines the rapidity of the bounding box detection algorithm and the accuracy of the triangle detection algorithm. The collision detection algorithm on the robot simulation platform is mainly used to prevent components from passing through other components during the operation of the robots, or to avoid the collision between the robots and the external objects. Most collision detection algorithms based on Web3D use bounding box detection algorithms, which will bring errors to the detection, but high-precision algorithms are difficult to run smoothly in the browser. Therefore, we add triangle detection algorithms to the bounding box algorithm and use it as a basis for judging whether there is a collision. What's more, we use molten code to speed up the traversal of BVH tree to achieve efficient and fast collision detection on the browser. In collision detection, fast collision detection usually uses the bounding box to replace the object itself, so as to achieve faster detection. The commonly used bounding box include AABB, that was an X-aligned bounding box, OBB, that was oriented bounding box, bounding sphere, and so on. These bounding boxes or bounding sphere have a faster speed in collision detection, but they will be obvious misjudgment, so they are usually used in the case of no accuracy requirements or as an auxiliary judgment method. Accurate collision detection includes triangle detection, ray tracing, and other methods. These methods can accurately judge whether there is a collision between objects, but they need a lot of calculation, so the acceleration method must be used to reduce the amount of calculation. In the robot simulation platform, bounding box is usually used to replace robot components for collision detection, because most use sims do not have high requirements for detection accuracy, and the collision detection based on hierarchical bounding box or octree can meet its requirements. However, for humanoid robots with many tiny joints need more accurate collision detection algorithms to judge. In the field of Web3D, the weak performance of the browser is difficult to support a large number of calculations. If we want to perform accurate collision detection on the browser, we must take more methods to reduce the amount of calculation so that the algorithm can run stably on the browser, and this is the main work in our paper. In our paper, we use molten code as a partition basis to construct a BVH tree. Molten code is a coding method that maps multi-dimensional vectors to one-dimensional vectors, which can preserve the local characteristics of coordinates in space. The calculation method and the actual effect are shown in the figure. Through this figure, we can clearly see that the sequence based on molten code has good adjacency in space. MBVH tree refers to the construction of the BVH trees by using molten code as a partition basis. In our paper, we construct two kinds of MBVH trees: robot MBVH tree and robot component MBVH tree. The robot divided by molten code is shown in the figure, in which different colors represent different nodes in the BVH tree. Through this picture, we can see that triangular surfaces of the same color are gathered together in space. The follow figure of collision detection algorithm based on MBVH tree are shown in the figure. Step 1. Using the ABB bounding box of the editing components to traverse the tree structure of the robots. Depending on whether it collides with the ABB bounding box of the editing component or not, the components that collide with the bounding box can be obtained. Step 2. Using the components obtained in Step 1 to traverse the tree structure of the editing components. After traversing all the components obtained in Step 1, the specific components in the editing components that collide with the ABB bounding box of the current components can be obtained. Step 3. using the specific components obtained in step 2 to traverse the MPVH tree corresponding to the components in step 1, and obtaining the triangular partial clusters that collide with the AABB bounding box of the component. Step 4, using the triangle partial clusters obtained in step 3 to traverse the MPVH tree corresponding to the components in step 2, and obtaining the triangular partial clusters in which the AABB bounding box collide with the triangle partial clusters in step 3. Step 5, using the triangle collision detection algorithm for the triangle partial clusters in step 3 and step 4 to perform accurate collision detection and calculate the results of the collision detection. Next, I'm going to show you the results and see how this will actually work. We select the joint we want to operate on the panel and then slide the slider to control the joint rotation. In the process of rotation, the collision detection algorithm will detect whether there is a collision. If there is a collision, it will stop at the maxed angle in the current direction. To conclude this presentation and the video, we proposed a lightweight robot collision detection algorithm for the Web3D robot simulation platform. This algorithm solves the problem of traditional collision detection algorithms, which is the difficulty of balancing the need for efficiency and accuracy on web browser applications. This suggested method can also provide technical support for the implementation of the Web3D robot simulation platform via detecting the collision in real time. Further research could usefully explore how to improve the performance of the platform and the algorithm. For example, GPU accelerating techniques can be included to accelerate detection speed. Retracing technology can be used to feel out possible collision before traversing MPVH. Designing a more efficient algorithm that can be implemented in the browser to judge whether two triangles intersect also is an optimization direction. We would like to thank our sponsor for this project, the Basic Grant of Natural Science Foundation of China, and the key project of Regional Joint Grant of Science National Foundation of China, and the Fundamental Research Funds for the Central Universities of China and the Shuangchuan Program of Jiangsu Province. Finally, I would like to thank you all for listening to this presentation, and if you have any question, please feel free to email either one of us.
Okay, thanks for the presentation. Are there any questions from the audience? Oh, no question. I have one question for you. Can you provide us some example of using a use case of using such kind of detection algorithm in the web? So which are the use cases for the kind of algorithm? Why in the web? This is my question.
Because with 5G and more popular or faster communication technology, we think web browser can cross platform, cross device. So any platforms in the browser can use we can use it without any requirement. If we use offline platform, we used to more we need more or we need to add software or others, but if in the browser we cannot, we don't need this, so we think on the browser we can make it more convenient for user.
Thank you. Thank you. I see one hand raised from the audience. Yes, so can you ask, please?
As me?
Yeah, yes.
Okay.
Yes,
Yeah,
sorry.
my question is that I got from the presentation that this is more about self-collision rather than collision, avoiding collision to the other objects. Is it true? First of all, and if it's not, so what is the benefit of your algorithm compared to very standard algorithms like A*, because they are also they don't need a lot of computation also. Also, if this is about self-collision, what is the benefit of your algorithm over analyzing the model of the robot? For example, as you showed, the purpose is just to avoid self-collision of the arm to the body. So an easier solution would be to limit the joint angle so that the arm of the robot doesn't get very close to the body. So what is the benefit of your algorithm compared to such traditional ways?
Because traditional methods are use bounding box, there will be some misjudgment. Because bounding box is use the box to replace the object itself, so it will have some space in the bounding box. But the method in our the method we proposed are based on the triangular surface. So triangle detection is use the triangle patches of objects. So the precision of it are 100%. It don't have any misjudgment.
Okay.
Okay. So do you want to? Or...
No. Please go ahead.
Okay. Well, because I am coming from a robotic background. Well, first of all, I can tell you that, you know, traditional methods are precise. So it's not that like 1 out of 100 robot collides. Otherwise, yeah, this is no good. Yeah, I'm still not convinced. Sorry for saying that, but I think that still traditional methods can avoid self-collision very effectively by analyzing the model of the robot and excluding all possible combinations of joint angles that cause self-collision. Still, I'm not convinced why to use your method over such methods.
Sorry, I'm.
So maybe we can continue this discussion in Discord. Because
Yeah. I just moved to the last question. There is one question from the audience.
For a long discussion. Yeah.
Maybe we can take the opportunity of the break to discuss more later this topic.
Yes.
Thanks. Thanks for the question. So
we can also create breakout room if we want, Alberto. Just in case you can move or you can leave the authors, speakers go directly in the breakout room. I created one earlier, but I don't know how I did that.
The question from the audience is in the chat is there a reason why you condition your work under humanoid robot collision detection? Do you think it's gonna apply to broader scenarios? Wengen?
Let me think.
Yeah.
This paper was under the background of a company provide the robot model for us, and he want us to do some research for this. So we do the research for so we do this research to solve the collision detection about the humanoid robot.
Okay, so we get your reasons. Okay, so this is the last paper of this session. We are just 3 minutes late, but I think we are in time. So we see you in 15 minutes. The session will restart at 10. So thanks again for the authors or the presenter, and see you later. Thank you.
I just have a very quick question. So if I understand correctly, recordings will be available in the future.
Yes.
Yeah.
Yes.
Sorry, it's like in this time zones on this side of the earth, it's like it's getting quite late. So I'm just gonna probably.
Yes, I perfectly understand you.
Thanks. Have a good one. And thanks.
See you. See you.
Well, hello everyone. We should be back. It's 10 o'clock. You can hear me well, right? Yeah.
Yeah.
Good.
Yes, yes.
Perfect, perfect. Thanks very much. With the Zoom, sometimes it's hard to know. Okay, so we will continue with our workshop in this second session that I will very happy to chair. And our second presentation, it's titled Application of Large Space for Investigating Pedestrians' Behaviors when Interacting with Autonomous Vehicles in Shared Space. And the presentation will be held by Andri Hanto from University of Tsukuba in Japan. I hope I pronounced everything correctly. So
yes, correct.
Andri, you can start whenever you want. You can share your screen and start the presentation.
So can you hear me?
Yes.
Okay, I will share my slide. Okay, thank you and nice to meet you all. I'm Andrea from University of Tsukuba, Japan. So on behalf of my co-authors, I would like to talk about the application of large space for investigating pedestrian behaviors, interacting with autonomous vehicle in shared space. So now the topic of autonomous vehicle has become popular in urban traffic safety. So focusing on the interaction between autonomous vehicle and pedestrian, we try to study pedestrian behavior. And in Japan, the elderly population will increase to 40% by 2050, and they remain active in society, as well as the shared space. Shared space have been developed around central cities to support pedestrians' movement. And studying elderly pedestrian interacting with autonomous vehicles in real shared space is challenging. So applying virtual reality promises to conduct a safe experiment to reveal helpful information for traffic safety. So in this research, we studied pedestrians' travel times, waiting times, and trajectories when crossing and walking to evaluate pedestrian behavior when interacting with autonomous vehicle. In addition, we investigate the perception of safety and the need for a human-machine interaction interface. So according to Timmerman, studying pedestrian walking behavior should consider two aspects. First, the choice of the next step, and the second is the choice of speed. Therefore, we design the scenarios by considering those aspects, crosswalk and walk straight. And we follow SAE, level 2 for automation to describe the autonomous vehicle behaviors in the low-speed commuter system. And we would investigate the acceptable speed and the need for the HMI interface. So there was no eye contact and communication between pedestrians and autonomous vehicle. And the shared space would be an environment without a curb or level segregating pedestrians and vehicles. And the speed limit range between 10 to 32 km/h. So we developed 3 scenarios for this experiment. So scenario 1, pedestrian crosswalk following path from A to B to C and finish at D. And scenario 2, following path D to C to B and finish at A. And both scenarios 1 and 2 differed in the car's direction when approaching a pedestrian. And the scenario 3 was pedestrian walks side by side, following path from E to F. And car would appear 50 meters from the center line. This is the center line, moving from right to the left along the x-axis. And participants were 10 males and 9 females, ranging from 66 to 77 years old, average 72.1 years old. And the environment mimics shared space around Tsukuba City bus station. And the procedure was done sequentially from rehearsal and 27 sets of scenarios with random speed. So, for example, set number 1 consisted of scenario number 1 with speed of 30 km per hour, and scenario number 2 with speed of 25 km per hour, and scenario 3 with speed of 30 km per hour. So in this case, the scenario sequence was fixed for each set as scenario 1, scenario 2, and scenario 3, and pair randomly with speed 30, 25, or 20. And finally, we distributed questionnaire at the end of experiment. So we utilized the large space facility to implement the experimental design. Large space is the largest encapsulated space with immersive display in the world. Continuously projected image on an immersive screen offer us sufficient room to simulate complex traffic situation in a shared space, as shown in this video. Sorry. So this video shows shared space around Tsukuba City bus station, and pedestrian is crosswalking when the autonomous vehicle passes. So large space, large space consists of 12 projectors and 20 motion capture cameras and 10 computers. The motion capture system provides the position and the speed of vision angle of participant using retro-reflective markers. And furthermore, cluster computers synchronize users' perspective in the virtual world, which allow us to monitor the motion of participants during the experiments. And we obtain data from simulator for drawing pedestrian trajectory and also calculating parameter. And first parameter would be the traveling time. So traveling time illustrated pedestrian moving time from start point to finish point. And from simulator data, we obtain the time for T1 and T2. So T1 is a starting time and T2 is the finish time. So therefore, we can get traveling time by subtracting T2 with T1 and waiting time for scenario 1 and scenario 2, and T2 with T1 for scenario 3. And from this chart, we can see both males and females did not significantly differ in time for each scenario 1, 2, and 3. So, however, we could say that the female participants walk faster than males. In addition, we found the survey, most of participants did not hesitate to crosswalk in front of autonomous vehicle and also walk side by side with autonomous vehicle. And second parameter is waiting time, was measured from when pedestrian notice the car approaching at the checking point. This is the checking point with the checking time TP until the vehicle entirely pass the collision point. So this is the collision point, and with the time of TC. Then we calculated the waiting time by subtracting TC with TP. And scenario 1, pedestrian could not notice the car approach because the car approaching from behind. And scenario 2 is the opposite side of scenario 1. And waiting time for scenario 1 range from 0 to 10 seconds, and from scenario 2 range from 0 to 7 seconds. And this graph, we can see that the average number of waiting for males and females, mostly they were waiting more at scenario 2. So the dark gray bar is scenario 2. When the participants saw that the car approaching, the increasing speed would increase the number of waiting. So those results show participants behave naturally waiting for a vehicle pass. And third parameter is the distance to collision point. Distance between the collision point and pedestrian path illustrated how pedestrians avoid autonomous vehicle by adopting a sloping trajectory. Males and females avoided collision point in average 0.2 meter, and from the survey we found that 55% of participants might crosswalk diagonally, and in this case the avoidance might not be because of autonomous vehicles interaction. And the last parameter would be the deflection angle. The deflection angle reflects pedestrian trying to assume a greater distance from the determined path. So this is the determined path from E to F. And then the actual distance, this is the pedestrian trajectories, pass close to them. And on average, males and females deflected their trajectory by 11 degrees and 11.9 degrees. However, they disagree with the assumption of always behaving like walking straightly. And the survey also revealed 79% of participants feel safe walking beside autonomous vehicle. So the deflection angle might not be because the interacting with autonomous vehicle. So I would like to conclude this presentation. So we confirmed that we could obtain data from large space facility, and we introduced the parameter for evaluating pedestrian walking behavior when interacting with autonomous vehicle in shared space. However, the result has not yet represented the elderly population in Japan due to the limited number of participants in this experiment. So we need to modify the vehicle behavior to investigate pedestrian behavior furthermore. Therefore, developing the facility will provide flexibility in designing the experiment. In addition, it also will enhance the quality of data. For next, we will establish the model for investigating elderly pedestrian acceptance interacting with autonomous vehicle. And the last survey revealed that 79 participants require communication with autonomous vehicle. However, they mostly suggested the sound like a beep beep to notify the vehicle existence. So thank you very much for your attention.
Thanks very much, Andre, for your presentation. We are actually almost on time for the next presentation, but maybe we have time for one question. I don't know if someone wants to have some question for Andre.
Oh yeah, well, one question, if it's possible. Just for maybe just one suggestion. Have you considered also the age, the age of the users? Because in your study, maybe you only consider the gender, male and female, but also maybe also the age of participants can have different in your parameters. And then the second suggestion is, have you considered the possibility to present in the immersive environment also some feedback about the behavior of the autonomous vehicle? So maybe the parameter that you observe can change according to feedback provided by the autonomous vehicle. So maybe the user are more prone to get close to the autonomous vehicle and so on. So just if you consider these two conditions for the experiment.
Also, thank you for the comment. So I would like to answer the first question. So actually, we studied about elderly pedestrian. So the age is from 66 to 77 years old. So they all males and female elderly people. And about the second question, yeah, maybe I will try to discuss with other authors about your suggestion. And yeah, maybe thank you for your suggestion about that. Yeah.
Thank you to you.
Perfect. So we have to go to the second presentation of this second session, which in this case is developing a VR simulator for robotics navigation and human-robot interactions employing digital twins by Silas Franco dos Rey Alves from Ontario Tech University, Álvaro Uribe Quevedo from University of Ontario Institute of Technology, Deloan Chen from University of British Columbia, John Morris and Sina Ratmar from GDK Systems. So, okay, you're super ready. So
yeah. Thank you so much for the introduction.
Yeah, so Silas, the floor is yours.
Yes, thank you. So just a quick background on the work. Like we are trying to provide high quality care to seniors and adults with developmental disabilities, which is a huge problem now because we have the aging population. So the number of people that we have to provide care is going to increase. They require personalized care and specialized care. And right now, with the challenges from the COVID-19 pandemics, we had limited access to the, oops, I forgot that the presentation has the timings. It has, we couldn't access the long-term care facilities, and also the long-term care facilities have limited resources to apply. So we are trying to investigate how emerging technologies such as service robots, VR, and artificial intelligence can help us to overcome these limitations. So to introduce what we're working on, like we have the Ether robot, which is a socially assistive robot developed to help seniors and adults with developmental disabilities to achieve a higher degree of independence, and also to assist caregivers by alleviating the burden of care. So we are collaborating with the Developmental Disabilities Association in Vancouver, and we decided to start the work with two main use cases: the safety inspection and the entertaining. So safety inspection would be having Ether to go around the long-term care facility, looking for falling people or objects in the floor, because basically anything in the floor is a safety hazard. And entertainment would be any kind of activity the robot do to the residents to keep them entertained while the caregiver can't give attention to them at the time. So the challenge that we are addressing in this work are the limited access to long-term facilities, that hinders the evaluation of the robot navigation, human-robot interaction. We also try to use the existing tools like Gazebo and ROS, but Gazebo specifically lacks VR components that could help non-specialists to participate in the development process, and also to do the research, like get into the simulation and provide a better human-robot interaction simulation. Also, we're started relying on open data sets to train the machine learning models, but they're also not very representative of the elderly population, nor they have natural falls to train our models. So Our proposal was creating the Ether simulation, which would support testing and assessing the robot behaviors and help us to detect virtual avatars for both HRI and fall detection. We didn't start working with this right now, but in the future, we want to start also generating synthetic data sets to help us improve our object classifiers and pose detection. And we built this on a previous work where we were using Unity Sensor SDK. We decided to get rid of it because it was slow and required a potent machine and had some issues because they had to replace the pipeline. We create new environments that replicates a space that we have physical access to, so we could test the robot in the physical and the virtual environment. And also, we performed the initial tuning of the robot navigation stack and to compare how the robot behave in the two environments. So we created 3 digital twins for this application. The first one would be the office space at JDQ Systems, which you see now in the screen. We also created a digital twin of 2 elderly people, and the virtual twin of the Ether robot that have all the sensors and actuators. Our system architecture have 2 computers, like the server computer runs the simulator and connects to the Oculus device using Oculus Quest. So the connection is through a USB 3 cable or through Wi-Fi. And the server sends the messages to the robot computer, which run ROS and all the software modules that control the robot. And we did this, we decided to use this architecture because we're using the same the same computer that you embed on the robot to run the simulation, meaning that the system will respond with the same performance. So this is an example of an interaction. So the voice interaction is done using Alexa. And here on the left side, you can see the robot navigation using the local and global maps. We are also showing the personal detection, and we are going to demonstrate like the face recognition. So just looking at some of the results, like we test the simultaneous localization and mapping using cartographer that was configured to build a map with a grid of 5 centimeters. Comparing the 2 maps, like you can see that the real map is much worse than the simulated map has expected. This is due to some missing obstacles that don't exist in the simulation, and also because we need to improve the accuracy of our simulation and introduce more errors. So for the first one, detection, we use the YOLO version 4 classifier using the OpenVINO implementation. And we used the original weights trained on the COCO dataset. And then we retrained that network using the following person dataset for 7,000 epochs. And then when we compared the results of the original data of the original weights trained only on COCO with or retrained on the following person dataset, you can see that there was an increase on the average precision, and recall for the intersection over union of 0.75 and 0.5. And the reason we didn't use only the following person dataset is because that dataset is very limited in the number of people they have, and also the environment. Like most of the pictures were with the same people in the same environment, just with different poses or in different angles. So as you see, we saw that the digital twins adequately recreated the real map, and the SLAN and navigation, the both real and virtual environments were the same with the same set of parameters. We tried the gesture detection with the controllers for puppeteering and testing the HRI, even though we didn't start using that yet for the simulation itself. The virtual avatars will speed up the evaluation of the fall detection behavior and also HRI. During this, you could save lots of costs associated with the real world testing, such as deployment and the test of different behaviors. And mainly because I am in Toronto, the robot is in Vancouver, so there's a 5-hour travel between the two offices. So that helps us a lot. And the current limitations are the accuracy of the sensor models. So we need to, right now we are using a Gaussian error model, and we need to get one that's more representative of what we would get in the real world. So just to conclude, like Unity and ROS allowed the simulation of robot navigation and person detection. We could replace the Unity sensor SDK to improve performance without sacrificing the accuracy. We were able to fine-tune cartographer for SLAM and also the move-based parameters for navigation. The YOLO version 4 could detect people and objects in the virtual environment. So this is promising for us to continue testing the environment with the simulator before we move on to the real test on the long-term care facility. And for future works, we will adapt the simulator to produce the synthetic data sets to help us to improve mainly the falling person detection, because there are no many data sets with those kinds of images. We also will introduce objects commonly found in the long-term care facilities, such as wheelchair, canes, walkers, and other stuff you will find on those places that you can't find in common data sets. And also, we are going to investigate the full bot tracking to test different HRI scenarios. So we can do activity recognition, for example, in the future. So thanks, everyone. If you have any questions, like we have the email ether@3srp.com or our website at 3srp.com.
Thanks very much for this interesting presentation. So I don't know if someone has questions for Silas. I have one. So I was wondering, so basically you're using this digital twin to test, how the robot navigates and detects whether, the patient has fallen. But have you considered using the same system, for example, for validating the acceptance of the robot by the users? Like, for example, I don't know, displaying different types of configurations for the robot for displaying the emotions, right? When he wants to communicate with the patient, etc. Have you considered using this tool also for that process, right? So just to understanding users' acceptability of the robots and so on?
Yes, so we did, and actually we started doing a pilot test not with the residents, but with the staff. So for that, we didn't use this simulator because at that time it wasn't ready yet. We used Outspace VR to recreated the long-term care facility environment, and we put the robot there and add some animations. So we brought people inside of the virtual environment and showed them the robot, the animations of the fall detection and some other behaviors that we were investigating at the time. And we got a very good reception. The only thing is that some of the staff, they weren't expecting that. So they were I can't say that we can use that result for the development yet. I think that there is a learning curve, and we have to be more clear about what we're expecting from them. But we are moving in this direction by implementing now a multiplayer simulator. So we can have the simulation running on one machine and different people using their clients, and there can be anywhere in the world, could enter the simulation and interact with the robot. So we are looking into that as well. So the idea is not only to test, like as I said, to the users, but also to communicate to our stakeholders, like what we're doing, the direction we are heading to, and where the project is.
Perfect. Thank you very much.
Thank you.
Maybe we have time for one more quick question. If someone wants to ask something else. Well, I think we are moving on to the next presentation. Thanks very much, Silas.
Thank you very much.
So our next presentation is Dentalverse, Interactive Metaverse Virtual Reality Implementations to Train Preclinical Dental Student Psychomotor Skills by Marcus Santoso from Digital Worlds Institutes in the United States, but we're not sure whether he's here. I think he's not here. I don't know if he had some problem connecting to the session, but anyway, we have the recorded presentation, so we will just play the recorded presentation.
With the impact COVID-19 has had on education, utilizing different methods of virtual learning has become a vital resource in replicating the same level of engagement experienced through in-person lectures. The College of Dentistry at the University of Illinois in Chicago is working towards the implementation of VR learning into standard lesson plans for first-year dental students. Continuing development from the previous year's efforts within the same application, our team expanded the program's features further by incorporating additional features available to the professor and students that promote student engagement. The student begins the simulation by choosing their avatar and entering the lecture room. Our team expanded off of the previous year's project and redesigned the layout to promote better flow through the space for VR users. Additional objects in the exam room that are seen to improve student immersion are the desking system and seating arrangement. The wristwatch user interface provides access to two features, the whiteboard and PDF file viewer. By facing their palm upwards, a user gains the ability to view this UI, which provides the controls for these two features. There is also a locking feature that can lock both the whiteboard and PDF in place so the user can access both with ease. The main button expands the interface's options, avoiding screen clutter if the user is simply moving their wrist. Upon expansion, the icons display or hide their corresponding features, ensuring correct orientation facing the player based on the head-mounted display's direction. Interaction with the wrist UI occurs through a finger tap, such as a press of a phone screen. But virtual reality currently lacks the feeling of pressing a physical screen. Haptic feedback in the form of light vibrations fills this void. Additionally, each icon acts as a feature toggle, meaning they change coloration depending on its current status. In a lecture room environment, a place for the professor to present slide presentations sits in the front of the room. The controllers are located at various points in the room, such as both desk and at the back of the room. The primary function implemented was the ability to host a multi-user application in virtual reality. Merging the work from the previous year's progress on the application, we further developed features that allowed users to engage different learning tools such as slide presentations, whiteboards, PDFs, and rooms that offer a place for users to take assessment tests. Expanding on this work's multiplayer functionality, the team has built a collaborative experience for professors and students in an updated virtual lecture room and exam room. For multi-user implementation, the team integrated Photon Unity networking too, remote procedure calls that send local data from one client to all connected users. This ensures the synchronization of objects such as surgical tools and the patient's mouth, along with displays like the slideshow presentation and whiteboard in either multi-user room. Utilizing an existing exam room from the previous project, our team transformed it to serve as a space for student users to take exams while maintaining immersion in the VR world. The student assessment room offers the user a place to practice dental procedures on a fake patient. When the player picks up the tool and begins operating on the patient, the controllers vibrate to create the sensation that the player is actually holding the drill.
Okay, so I think the authors of this paper haven't connected to the session, but anyway, at least you get some idea of the study, and obviously you have the full paper, and if you need the contact of the author for further questions, we're happy to provide you with the email, and we will move on to the second presentation, which is investigating light quality in office workstations, a combined approach utilizing virtual reality and physical workstations by Roxana. I don't know if I will pronounce your last name correctly.
Jafari. It's fine.
Jafari from Lawrence Technological University in the United States, and also co-authors with Piers McNaughton from View Inc. in the United States also, and Alina Osnaga, also from Lawrence Technological University. So Roxana, you can, the floor is yours for your presentation.
Okay, do you see my screen?
Not yet, but you're sharing. I can see that you're trying to share, but I cannot see the screen.
Okay, I've shared the screen, so whenever you can see it, please let me know. No?
No.
Yeah, maybe you should try to reshare it again. It doesn't seem to work.
Okay, how about now?
No. Are you using two screens or something like that? No.
No. I'm using one screen. So maybe Alina, she is my co-presenter. So Alina, maybe you try sharing.
Okay, yeah, now we can see it.
Okay, awesome. Thank you so much for joining this presentation. Well, in this presentation, we looked at lighting quality in office workstations using a combined approach, utilizing virtual reality and, of course, measurements in physical workstations. And well, if you go to the next slide. Well, this project was a collaborative effort between research teams from College of Architecture at Lawrence Technological University, or LTU, in Michigan, and View Inc. The research team at LTU College of Architecture focuses on improving user experience in the built environment using human-centered design. And the View Inc. research team investigates implication of smart windows and their impact on improving occupants' health and productivity. So we decided to collaborate on this study together to look at the impact of different daylight control systems on occupants' visual comfort and satisfaction in virtual and physical office environments. So we did this study in a physical office work environment as well as a virtual one. We have our co-presenter Piers from View Inc. I'm not sure if he's present right now, because I saw him earlier. If he's not, I'm going to go ahead with explaining the physical. I think we lost him in the presentation. So in the first phase, that was basically conducted by the View team researchers, 5 different daylight control systems, as you can see in the picture here, were installed in an office environment located in Mississippi in the United States. These daylight control systems included 4 shades with different openness factors that allowed different transmittance of daylight, and 1 electrochromic glass with 1% of transmission for the visible light. And if you go to the next slide, you can see the digital twin in the previous slide. you can see the digital twin that we actually created in the office environment. So this is the actual office. And if you actually look at the link, if you search the link over here, you can basically go and explore the web browser. So I'm gonna try to share my screen with you. If possible, I'm gonna try again so that you can actually explore this web-based digital twin of the office environment that we actually conducted. Hopefully this will work this time. And if not, you can explore it for yourselves using the link provided. I'm going to reshare it in the chat portal as well. So can you see my web browser? Okay, great. So this is the digital twin that we created of the office environment after we installed the different daylight control options. And there's a link to VR. So if you hit the link and if you have Oculus Quest 2 headsets, you can basically connect it directly to your VR headset and experience the immersive virtual environment for yourself. If not, you can basically use your cursor to look at different daylight control options that we had in this office environment. So we recruited participants in the actual office environment and the virtual one to basically go to each of these workstations. And we assigned them with an online survey to get their feedback and understand which one of these daylight control options they would actually prefer in the office that they experienced. And this was the electrochromic glass option that they were exposed to, as opposed to the dark shades. So going back to the presentation.
Roxana, do you want to try again with the presentation?
I'm going to try again sharing. Hopefully nothing will go wrong. Yes, perfect. So we actually recruited 112 participants in the actual office workstation. They were randomly assigned to these stations and fill out a survey. We also created the digital twin, as you saw, and we brought it to the LTU campus in Michigan, and we recruited 61 participants who were randomly assigned to these workstations. So basically, we wanted to find the response to the following research questions. We wanted to see how different daylight control options impacted perceived visual and thermal comfort and satisfaction with lighting quality and views in the office workstations. We wanted to see how these different daylight control options could impact overall satisfaction with the office workstations. And also we wanted to investigate the differences and similarities in evaluation in the physical office versus the virtual office. And this is what we found. So based on the measurements that we conducted in the physical office, we noticed that the visual comfort based on daylight glare probability differed for each of these daylight control options. The electrochromic or EC glass performed best, as you can see here. And after that, the dark shade performed well. But as you can see, the other shading options did not perform well at all. And actually the 10% dark shade was the worst one of all. And we also measured the desk temperature in front of each of these workstations. And we noticed that compared to the EC glass, all the other dark shades actually cause a lot of heat on the desk surface. And the 1% dark shade was actually the hottest one of all because of the fabric and the dark color of the shade. Then we looked at the survey results to actually understand which daylight option was scored high compared to the other ones. And we also looked at the VR and physical office evaluations to understand if there were any variations in the ratings. So each of the variables that you can see here, for example, here, the natural lighting quality, satisfaction with the lighting quality was rated. The ratings were on basis of a 5-point Likert scale, with 1 being a low rating and 5 being a high rating. And we combined scores of 4 or 5 as a high rating. And this is what you can see here in the graphs. So based on the analysis, you can see that the EC glass was scored highly, but for the other ones, there are variations. And same for satisfaction with the view, we noticed some variations in how these daylight control options were evaluated in VR versus physical offices for visual comfort and interestingly for perceived thermal comfort. We noticed that, for example, the EC glass was perceived thermally comfortable in the physical office, but when it was presented in a VR and we asked participants to guess whether they would feel comfortable in this office workstation, they did not rate this option that high as opposed to the physical office workstation. What was interesting to us was that despite these variations, when we looked at the overall satisfaction with the workstations, there was an interesting agreement between the physical and VR office, and that was that in both evaluations, the EC glass was actually the winner. As you can see, it received the highest mean satisfaction score on a 10-point scale, with 1 being unsatisfied and 10 being satisfied. You can see that the score was highest for the sliding option. And this is the summary of the interesting things that we found and the differences between the physical office measurements versus the virtual office measurement. You can see that based on the evaluations that we had, the EC glass basically outperformed all the other shades in the physical office environment. And when we looked at the VR office, we noticed that the EC glass over here also performed really well, but there were variations in evaluation of, for example, perceived visual comfort or satisfaction with outside view. We noticed that, for example, the dark shade with 5% opening factor also performed well. To have a more in-depth insight into how participants perceived these two daylight control options, we looked at the interviews that we conducted after the VR experiment. And Alina is going to now go over the interviews and let you know about what we found.
During the interview content analysis, as Roxana mentioned, we noticed that the EC window was...
Alina, we cannot hear you well.
Can you hear me now?
Yes,
now it's better. Now it's better. Yeah.
So during the interview content analysis, as Roxana mentioned, we noticed that the EC window was rated highly in the physical office for visual comfort. The participants who experienced it in the VR reported glare as a potential problem. So, for example, one of them said that at certain times of the day, there could be a lot of glare. And this is exactly what they could see in the VR when they were experiencing this workstation. On the other hand, when they experience a dark shade, which we know based on the field measurements that we conducted, dark shade 5% caused perceptible glare in the physical office, the comment in the VR after experiencing it also showed some potential visual discomfort due to clarity. However, the severity of the glare was pretty much underestimated in the VR environment. For example, one of the participants said it was a little uncomfortable, but I still enjoy it. And another one said maybe a little bit more glare reduction would be necessary, but the glare wasn't that bad. So it seemed like they did not have a quite good perception of how severe the glare was. As a conclusion, the EC window was rated highly compared to the dark shades for user visual comfort and light satisfaction in both physical and VR environments, while dark shades caused warmer desk surfaces temperature compared to the EC windows. The majority of participants assumed that the EC window will lead to higher temperature in the VR. And they reported that glare could be a problem as well. Regarding the overall satisfaction, the EC window outperformed all the shades in this category in both the physical and VR environment, which was really interesting to us. And regarding the differences and similarities between the virtual and the physical environments, we noticed some differences most likely because technologies probably cannot accurately represent the intensity of the sun and may minimize glare. And although we use Matterport and we created a digital twin with the actual data control system in space, still the degree of visual realism was not to the point that they could understand the severity of the glare. How can we use this further? This information we consider is very important for the designers and the architects in the industry when they want to use VR as a tool to obtain user feedback during the design process. Or when the project is not constructed yet, it is very important for us to know how the VR works in our favor and to what degree we can actually rely on a VR tool during our design process. It's also necessary for students to be familiarized with this tool and understand to what extent it can help them in the design decisions. Thank you very much. This was our presentation. And if you have any questions, don't hesitate to reach out to us and we will be happy to open the discussions.
Thank you so much. And thank you for bearing with the technological difficulties.
Thanks very much for your presentation. Actually, Shu1 in the chat, he's asking if you can share the link. So you, absolutely. Yeah, so if you can, they're curious probably to try this with VR, I don't know. And I don't know if someone has some questions for Roxana, Alina, and Piers.
I just shared the link to the model, and if anyone possesses virtual headsets, they can have an immersive experience as well.
Well, I have a question, maybe a more technical one. I don't know if it makes complete sense or not, but so it was really interesting, these differences you found between the virtual environment versus the real one. And I was thinking, wouldn't be any method to render the scenario in another way that maybe can, I don't know, wouldn't this difference come from how you're rendering the scenes or how you're trying to simulate the lightning itself? Maybe there is some technique or from the technical side that could overcome these limitations, and then you would get like a real digital twin, right? Because your results seem to indicate that it's not a, let's say that the reliability of the digital twin is not 100%, you cannot trust it 100%, right? So I don't know whether you have come up with some possible technical solution for the future.
So this actually, in the architectural field, we usually use some simulation tools, like for example, Revit or Rhino to simulate light. However, in this case, we did not simulate light. We actually installed the actual models in the office environment, and we did a 3D imagery using a Matterport tripod cameras to create a digital twin of the model. So this was actually one of the ways that we could increase the visual realism. And despite that, compared to the conventional methods of creating, for example, simulating lighting in the architectural tools, we still notice some discrepancies in the results. And Piers, do you have anything to add?
Yeah, I was just gonna, well, great job, Roxana and Lena, on the presentation. It was really good. I was just gonna add too that, you know, in most scenarios, you don't wanna create glare, especially in VR, where it can already be a somewhat disorienting technology. And so I think by design, they've been trying to, you know, limit some of the instances of glare. I know there's a lot of applications in gaming where some of the users might be pushing for that, but it can lead to real discomfort. And so that's why I think we've seen the technology not go there, even though it might be feasibly possible. Another thing that I'll just share too, maybe I can share my screen, is in addition to having the Matterport type imagery, something that we're working on at View is turning our windows into displays themselves. So you can start bringing some of that onto the skin of the building. So I'll show an example of that just so people can see what it looks like. Can you see that?
Yes.
So this is another way in terms of augmenting an experience in a building, as opposed to having it be all headset based. You can use the actual facade of the building itself and augment onto the windows in a way where if you want it to be, it can be a window to the outside. or it can be a collaborative work surface, or it can be kind of a surrounding augmented video type of experience. So something we're excited about when we think about additional ways to kind of blur the lines between reality and virtual reality is kind of creating these types of experiences. And I'll post the link to the chat in case people want to learn more.
Very interesting. I was also wondering, maybe the Vergence accommodation effect of just having the glasses on your eyes, or maybe might play some role in the discomfort, well, in the ratings, and maybe evoke some discomfort that might influence ratings. But yeah, it's just so yeah, we're good on time. I don't know if someone else wants to make Alberto. Yes.
Yes, if I correctly understand, during the presentation, you showed the graph representing data, and if we focus on the virtual reality data, we can observe a very large standard deviation if I get the graph and the meaning of the graphs. So I just want to ask, in your opinion, which are the reasons behind this very high variation of the data for the virtual reality and not for the physical one scenario? If there is something that can help or can improve the virtual reality setup.
Well, yes, that's true. So if you look at the standard deviations, especially for the overall satisfaction, we noticed larger variations for the virtual reality. And of course, this was our preliminary analysis, and we're doing more analysis on this data to understand, for example, how do demographic information that we collected from our participants, like age, for example, age is an important variable, can play a role in how they actually evaluated those options in virtual reality.
Yeah, and the two other things too, Alberto, on that, in the physical space, we had almost twice as many people, so that helped bring the error bars down. I'm sure if we looked at a sample of 50 or so people, it'd probably be more similar to what Roxana found. And the second thing too is we did a within subject design versus between subject, and so from a statistical standpoint, that helps bring the error margins down because you can control for some of that interpersonal differences. The trade-off though is that then everyone is exposed to all conditions, so they might be potentially biased by having seen two things already before they do the third iteration. So they went through all 6 of the workstations in order, whereas with Roxana, they exposed each person to individual conditions so that you wouldn't have that kind of crossover bias. So 2 different ways of doing it, but I think we should also emphasize that the results actually did have a lot of similarities. There are 1 or 2 areas, like Roxana mentioned, where maybe for glare or thermal comfort, it wasn't able to copy over very well. But when it came to views and overall satisfaction, the results are actually very, very similar. So we were encouraged by that.
Thank you. Thank you for the reply. Thank you.
Thank you very much for the presentation. So we're moving on to the last presentation of this workshop, which is titled, "Are You Seeing What I'm Seeing? Perceptual Issues with Digital Twins in Virtual Reality," by Brian Adrian Flowers from Aptima and Summer Rebensky from Aptima. So Adrian, hello. So you can just share your screen whenever you want and start the presentation. We cannot hear you.
I am sorry. I
know we can
mic
hear
muted.
you. Perfect.
That's embarrassing. Can everyone see my screen?
Yes.
Great. My notes are below me, so I'm going to look down. I apologize for being rude by not looking directly at the camera. So, hello everyone. My name is Adrian Flowers. I'm a senior research engineer at Aptima. And today I'm going to be discussing known perceptual issues in virtual reality and how they can affect the application of digital twins and within virtual environments. So to start with, why are virtual reality digital twins important? All right, so in short, integration with virtual reality enhances the breadth and capability of digital twin systems. Through this integration, users are able to train, test, and refine given systems with an increased focus on things like real-world workflows as supported by these environments, which is fantastic. it can provide a lot of direct and actionable benefits to users. However, virtual reality systems, particularly ones that use stereoscopic head-mounted displays, will distort human visual perception. And because of this, users interact with these digital twin systems in an environment that does not properly reflect the real world and can affect what they gain and input into the system. So in the next section, I
just have one question. You're changing the slides or you're just on the same slide all the time?
Oh, I am sorry. I have a duplicate of my slides up.
I was guessing that you were changing. No, don't worry. It's because I thought you were changing. You wanted to change slides, but we couldn't see it. Okay, good that we solved it. That's it.
Thank you for catching that.
Don't worry.
As I was saying. Yes, in the next section, I'm going to discuss some well-known perceptual distortions that affect VR systems. And then I'll wrap up with some known behavioral consequences of these perceptual distortions and the types of effects they can have on users. Right, so far I'm good on time. So first, I'm going to start with a discussion on field of view. So without impairment, humans generally have some approximate foveal field of view of somewhere between 120 to 140 degrees, right? However, most commercial, VR head-mounted displays impose a significant constraint on the user's field of view, which can have a number of direct and indirect effects. Though there are a couple ultra-wide VR headsets on the market, which will extend the field of view closer to what humans actually have. But some preliminary research suggests that issues related to visual distortions in the periphery of these headsets could exacerbate certain phenomena such as cyber sickness. So you can have the ultra wide view if you need it, but you might have other issues as well. Okay. Next, I'm going to talk about one of the more famous ones, verges accommodation conflict. It's a bit technical, so I'll try to summarize it and hopefully not do too bad of a job. So the method used by stereoscopic VR headsets to project imagery interferes with the normal process used by the ocular system to focus on objects. When your eyes focus, two processes take place. Vergence, which is where your eyes rotate to keep the object you're focused on in the center of the eye, as shown in figure A. And accommodation, which is when the lens in your eye changes its shape to capture the appropriate level of light from the object you're focused on. Now, the amount of light your eye needs to receive, which will determine the shape of the lens, is dependent on the distance to the object. And so right there, we can directly see what the problem is. If you're using a stereoscopic VR headset, vergence is simulated by changing where the object is projected for each of the respective eyes. So your eyes are going to rotate properly. However, the distance from your eye to the lens is static and unchanging, which means that accommodation does not need to adjust even when you believe the distance to an object is changing. And because when you're using a stereoscopic VR headset, your eyes will still rotate, but they no longer need to adjust for the distance to the light, that is going to break your normal vergence accommodation process. And that is called vergence accommodation conflict. It's known to cause a number of fairly short-term issues, such as eye strain, headache, and visual fatigue, amongst others. Now, because I spent a lot of time on this slide, I'm just going to go to the next one. The third perceptual distortion I'm going to kind of highlight would be ocular vestibular mismatching, which anyone that does development or has experienced VR system is going to be fairly familiar with. And forgive me for reading off the slides a bit. So the vestibular system located in the inner ear assists with balance and spatial orientation. Similarly, the ocular system helps with the correction of balance and spatial orientation. So VR headsets provide input to the visual system, but not the vestibular. And so you can have misalignment from between these two systems, right? Like if you imagine that you're on a VR roller coaster, your eyes say, I'm going downhill, but your inner ear says, I'm sitting in a chair. Now, this is, of course, a very long-standing research issue as to the effects of this misalignment, particularly to the extent to which it affects things like, cyber sickness. And the final perceptual distortion I want to highlight would be environmental cueing, which is the human visual system makes use of environmental cues to assist with characterization and understanding within one's environment. So this can include things like estimating the distance to objects and the spatial relationship between objects by using things like shadows, right? Or a binocular cue based on how objects move as you adjust your eyes. So all of these visual cues are not going to be directly replicated in VR. Some may not. And so it's also believed that that can have an effect and degrade one's understanding of relationships and objects within virtual environments. And so the big tech dump, a lot of phenomena. What does it matter? Why do we care? And so I just summarized a couple of the known and suspected and potential behavioral consequences of these and other effects on a table in this slide. Right. So starting from the top, you have things like misalignment, spatial misalignment, and misaligned object relationships. So users in VR are known to have difficulty estimating or understanding relative size and space between objects. And so if this is impaired, it becomes particularly problematic for digital twin simulations that necessitate making decisions in relationship to perceived distances to threats or risks, such as things like testing driver or pedestrian safety systems. A second one includes things like alterations to visual search strategies. Users using a stereoscopic display have to modify how they search for objects in virtual environments. A big part of that being due to things like a reduced field of view, right? Because users do not have a wide field of view, they have to modify how they're looking for very specific visual stimuli. So this change can be particularly problematic when users are doing some type of visual search, or if you're testing out visual search assistance, target or object identification systems, because their performance when using a system within a virtual environment is unlikely to match the performance with the system within a real world environment because of changes to the visual search strategies. Virtual reality may also alter things like navigation and pathing strategies, in part due to changes in the field of view. So this is of concern because things such as mazes or complex virtual environments are sometimes used to test navigation assistance systems and study human behavior. And if the user's navigation strategies are impaired or altered, it can impact the validity of these tests. So luckily that one in particular isn't likely to be a major issue, but it is fairly understudied. And so it could be problematic, it could not be problematic, but it is important to mention. All right. Virtual reality will also impair a user's balance, which can be of concern when users are interacting with systems that augment or driven by a user's balance. I've seen studies on things like using virtual reality to train use of surfboards and surfing simulators. And because when a user's in VR, they're no longer going to have accurate visual input in some ways, it can cause a minor effect. And then the final one I'm just going to mention is potential for impaired decision-making. Some studies suggest that right after using a VR system, a user's ability to make decisions is going to be, it's going to take a bit longer. Not a major impact in most use cases, but if you are testing or evaluating a system and one of your test metrics is something such as decision-making time, that can impair the results. And so that was just kind of a quick survey and overview of these perceptual issues, how they can impair applications. And I do have some things related to mitigations where they are known. But I am out of time, so thank you everyone for listening, and feel free to ask any questions. Of course, here's my contact information if you'd like to send me an email for follow-up questions.
Perfect. Thanks very much. I don't know if someone wants to ask a question to Adrian. No questions? Well, Adrian, I found that it was a quite useful summary of many of the limitations we currently have with the VR. I think you did a nice summary of things that we need to find some solutions, and some of them are really tricky, right? I think in terms of navigation, did you propose some type of solution or not in your slides with the visual vestibular mismatch?
Let's see.
So you said nothing to add, but actually now there's a lot of techniques right now in locomotion and so on to try to overcome.
Yeah, no, there are definitely a number of techniques to resolve or mitigate many of these issues, especially with kind of like view focal strategies. Now, in terms of navigation, I don't know of major mitigations for that one, but that one is also somewhat on the periphery of VR research. You find it much more in terms of looking at eye degradation. So that one is fairly understudied, I would say.
Okay, so thank you very much for your presentation, and we have come to the end of the workshop. Thanks very much for attending. I don't know if Fabrizio or Alberto want to add something as closing words for the workshop.
I just, sorry.
Yeah, please, Alberto. No, please, of course.
Just want to thanks again all the presenters that are here, that they share their ideas, their very interesting contribution, and thanks again for all of you.
Yes, I think that we really had a complete picture of everything we wanted to see in the context of this workshop. I think most of the perspective have been tackled. So really, I think speaking also on behalf of the other two organizers that are not attending today, I think that you did really a good job with your papers. And of course, we're really looking forward to see you around in the conference. And of course, next year, should this workshop will be organized again. Of course, we will propose it again. So hope to see your contributions again. Bye-bye. Good night for those who are in Europe or in Asia, and good morning, everyone. Bye-bye.
Thank you so much. Bye.
Bye-bye.
Thank you.
Thank you.
Bye.
Bye-bye.
Well, bye-bye.
Bye-bye. Hello.
See you.
See you.